Okay. All right, we'll get started here. The test results that I have graded are generally pretty good. I haven't graded you guys yet in the high schools, but that'll be a priority, and I should have those grades posted by sometime tomorrow, and I'll send out an email when they are posted so that you can go look and see what your score is. The homework and take-home quizzes, I've started to grade some of the take-home quizzes, but I want to make sure to get the test done first. So I found that the bonus points did help people considerably, so I'm glad that I had that option for you guys. There's another homework assignment on the new chapter that we're starting, Chapter 11, and it covers the first 3 sections of it, and that is due on a week from today. And hopefully you guys are going to be getting a hard copy of that this morning. If not, it's posted on Blackboard, and you can print it out from there. Okay. And if you have any concerns about the test, you'll need to contact me individually, so I'll be glad to take your questions on any of the tests grading. All right, so we're starting on something completely different. We got to start on it on Monday. Of course, that was before the black cloud. Now the black cloud has passed, and we can focus maybe a little bit better on this. This whole chapter talks about sequences and series and power series, and talks about representing functions as a power series. That's towards the end of the chapter. But it starts out with this concept of sequences. And as we saw on Monday, a sequence is a list of numbers. That's all it is. And it can have a limit. If the limit, and we usually designate them as a sub n, if the limit of a sub n as n goes to infinity, it's an infinite list of numbers. If it equals to some finite number L, then the sequence is said to converge. If it does not equal to a finite number L, then the sequence diverges. Okay. Now, we went through this fact here, and this is something, again I'm putting an asterisk by this fact here. We're looking at the limit of some number r taken to the nth power as n goes to infinity. So this would be r to the first power, r to the second power, r to the third power, r to the fourth power, etc. That would be the terms of the sequence, just plugging in those values for n. Now, if the absolute value of r is less than 1, these keep getting smaller and smaller and smaller, so therefore the limit is equal to 0. If r is equal to 1, then of course we know that 1 taken to any power is 1, so the limit is equal to 1. Otherwise, it diverges. All right, we'll use that fact for the next section. And then there's another fact here from that we had mentioned is this. If the limit of the absolute value of the terms of the sequence is equal to 0, then the actual sequence, the limit of the sequence itself as n goes to infinity equals 0. All right, things get squeezed around 0, and so it just equals 0. I'll put a little asterisk by that also. And then finally, we had a third fact, and that's this. If each term of the sequence, a sub n, is equal to a value of a function at some integer n, so this is some function, and if the limit of the function as x approaches infinity is equal to some finite number L, then the limit of the sequence as n goes to infinity is also equal to L. So what we have here is that each an is, say, we take a function and we plug in n instead of the x. For instance, we could have 1 over n squared. Our underlying function for this would be 1 over x squared, all right? The sequence just takes on the values when it is an integer. And we know that the limit of 1 over x squared as x goes to infinity, the denominator keeps getting bigger and bigger, so it's equal to 0. So therefore, the limit of a sub n as n goes to infinity is also going to be equal to 0. Okay. Right. All right. Then the new thing that I want to talk about then today is called the squeeze theorem. And I've got a slide here to show about it. But let me just put some English down here on the paper here. And basically this is this. If one sequence, we'll call it B sub n, just use a different letter of the alphabet, is quote unquote squeezed between two other sequences, let's call those A sub n and C sub n, and the limit of A sub n is equal to L as n goes to infinity, and say the limit of the c sub n as n goes to infinity is L, then this sequence that's squeezed between them is also going to have the limit L. Then our conclusion can be the limit as n goes to infinity of the sequence in between is also going to be L. And let me just show this, a visual on this and let me get you guys where you can see the computer. Okay. So what we have here, we have actually three sequences here. We've got up on top in blue a c sub n. Up on the bottom we have a sequence a sub n. And in between those two, we've got a sequence b sub n. And notice the values of b sub n are between the other two sequences. The c is bigger, the a is smaller. Yeah, Jenna?
Okay, so the only way we would know that they're between is if we graph them, or is there a way to know?
No, we can figure out another way besides graphing them. So the question was, is the only way to figure this out is to graph them? And no, we can figure this out using some algebra, okay? So we don't have to be graphing them. All right, notice then the c sub n seems to be going to some value, whatever that value is. A sub n is also going to some value. It looks like it's the very same value. So therefore, this sequence that's squeezed in between them has to also be going to that same limit value L, all right? So that's really all this theorem says. And I think that's a good visual to show that, okay? All right. You guys, let's get this down. And, okay. All right, let's look at a couple of examples of the squeeze theorem. And Jenna, you're going to see that we don't have to be graphing them to figure this out. Okay, examples. Let b sub n equal the cosine squared of n what do I want to have there? Of n times, I don't like that. Okay. Let's put n times 3 divided by n squared. Okay, that's our b sub n. And let's look at this now. Okay. What's the biggest value that the cosine squared can have? 1. Remember, cosine and sine are both between -1 and +1, right? Right. So therefore, cosine squared, the biggest value it can have is +1. So we can say here that cosine squared of 3n, no matter what the n is going to be less than or equal to 1, can't be bigger, and it can't be smaller than 0, right? The smallest value of when we square it, we're going to get the smallest positive value we're going to have is going to be 0. So therefore, we know that if I divide then all of this by n squared, our sequence is squeezed between well, this left side is just 0 all the time. 0 divided by any number is 0. It's squeezed between 0 and 1 over n squared. Okay? So we can look at this as our, say, our c sub n, and this is our a sub n. It always has the same value of 0. Now, first of all, do we see how it's squeezed between these two sequences? Because cosine squared is going to be between 0 and 1. All right. Now, this sequence, as n gets bigger and bigger, what does 1 over n squared go to? 0, because we're having a denominator get bigger and bigger and bigger. So that limit is 0. Well, 0, if it's just plain 0, that also goes to 0. So both the bottom and the top sequences go to 0. Both the bottom and top sequences have the same limit, 0, as n goes to infinity. So we can use the squeeze theorem and say, by the squeeze theorem, the limit as our n goes to infinity, let's see, what is it? Cosine squared of 3n divided by n squared, its limit also must be 0. Okay. So that's one example. We didn't have to graph this thing. Yep?
Are we ever going to have something that, like, maybe they both don't go to the same number?
Where they both won't go.
What if one was 0 and one was 2? Are we ever going to have that?
Where one goes to, oh, you mean where the top, the squeeze theorem would not apply. If the top sequence goes to, say, 2, the bottom sequence goes to 0, you can conclude that it has a limit, but well, no, you really can't. You can't really conclude anything if the top limit is different than the bottom limit. All right? Okay. Now, let's look at just one more example here of the squeeze theorem. Here, our b sub n is equal to the sine of, let's say, 4 times n divided by n to the 3rd power. Now, notice the difference with this one is this isn't squared up on top. It's just the sine. All right. Now, we know that the sine of 4n, no matter what that n is, cannot be bigger than 1, so it's less than or equal to 1, and the sine can go down as far as -1. So the top there is squeezed between -1 and +1. Now, if I divide all of these 3 parts by the n squared, let's see what we have here. The n cubed. Oh, thank you. N cubed. Yeah, I changed it. All right. This is our sequence, the b sub n. Now, this one, the top one here, we could call this our c sub n. This one, as n goes to infinity, it equals 0. Again, we have bigger and bigger numbers in the denominator. And what about this one? Even though it has a minus sign in front of it, as n gets bigger and bigger, what is its limit? -1 over n cubed. It's also 0. Okay? Because remember, we can say if the limit of the absolute value of it is equal to 0, then the actual limit of -1 over n to the 3rd is also equal to 0. All right, and that's what we have here. And we can call this our a sub n. So again, we have that our b sub n is squeezed between two sequences whose limit is 0. Thus, we can conclude by the squeeze theorem that the limit of b sub n, let's write it out, the limit of sine of 4n divided by n cubed as n goes to infinity must also equal to 0. Yeah?
How did you get the 1 in there?
Well, can Can sine be bigger? Can sine, it's the value of sine, what does it range from? Okay, I'll push it. No. Sine can be negative. The sine of 3 pi over 2 is -1. Sine ranges from -1 to +1 in potential values. All right? So therefore, yes, so therefore I'm putting my -1 and my +1.
Can you just go, so sine's -1 form, what's cosine and tangent?
Of what?
What can they go from?
Okay, let me ask you that.
Well, I think it goes back to -1 to +2.
Absolutely. Cosine ranges from -1 to +1. Okay, this isn't going to become a trig class, but what's the sine squared of x plus the cosine squared of x equal? 1. How can sine and cosine ever have a value more than 1? They can't. What about tangent? What about when x is approaching pi over 2, 90 degrees? What's that tangent value approaching? It's the sine over the cosine. Don't say that. Don't say that. It's approaching infinity. It's sine over cosine. Right? Okay. Cosine at 90 degrees is what? Right. So therefore, this limit is infinity. We're dividing by a small number. So tangent has no limit on its values. It can be anything from -infinity to +infinity. It has no limit. Okay? All right. Sometimes with these problems, L'Hopital's rule has to be used. So sometimes L'Hopital's rule is needed. So let me show you an example here. Let's find the limit, again, as that n approaches infinity, of the ln of n divided by n. This is our a sub n sequence. Now, we know that the ln, as its arguments get bigger and bigger, that goes to infinity. And we also know here that n, the denominator, is also going to go to infinity. So guess what? We have an infinity divided by infinity case here with trying to figure out the limit. All right? So, the function we need to look at is what function? The ln of x divided by x. And see what its limit is, and see what its limit is as x heads to infinity. All right? We have to use L'Hopital's rule with a regular function with an x value. So we just basically look at our sequence. It's the ln of n divided by n. Just replace the n with an x, and we have the ln of x divided by x. So the limit as x approaches infinity of the ln of x divided by x, both it's infinity over infinity case. So we can, let me put an h there for applying L'Hopital's rule. So we can look at the derivative of the top over the derivative of the bottom. So the derivative of the natural log, so this would be the limit, again, as x goes to infinity. The derivative of the natural log of x is 1 over x. The derivative of just plain x is 1. So we then have the limit as x goes to infinity. 1 over x divided by 1 is just 1 over x. So again, the denominator is getting bigger and bigger and bigger, so this limit is 0. So we can conclude then that this sequence which is the same thing except it's only at the integers, this limit is also equal to 0. So we had to do a little bit of extra work there because we had an infinity over infinity case. Okay. The last thing in this section is about applying a continuous function to a sequence. All right, and it's not as bad as it perhaps sounds. Applying a continuous function, and we'll show a couple of examples of this, to the terms of a sequence. Notice that all of these questions on sequences are about either finding its limit or saying whether it doesn't have a limit. That's what all your homework is about. Okay, so let's look at this example. We're going to find the limit as n approaches infinity of the sine of pi divided by n. Okay, so this is our sequence here. This is our a sub n. But we're applying this function to it. We're applying sine to it. Now, it's really easy to figure this out. What I basically do is put the limit inside the parentheses. So what I'm going to do here is put the limit inside the parentheses. So this is then going to become the sine, and then I'm going to have a big set of parentheses here, and now I put the limit in on the inside, the limit as n approaches infinity of our sequence pi over n. That's what I mean by putting the limit on the inside of the parentheses. Now, what's the limit as pi divided by n? What is that limit of this as n gets bigger and bigger? 0. Right. Again, so much of this is just realizing you're just dividing by a bigger and bigger number, and you have 0. So therefore, this inside limit here is 0. So this is going to be equal to the sine evaluated at 0, and that is what number? 0. I'm going to shame Jenna into getting this trig down pat. All right. The sine of 0 is 0. All right. And that's our limit. Okay. That's just how we found it. Let me do another example, which is a little bit more challenging. The limit as n approaches infinity of the tangent, of, on the inside of the parentheses, we have 2 times n times pi divided by 1 plus n squared. Okay, we want to figure this limit. Again, I'm going to put the limit inside the parentheses. So I'm going to write my tangent first, big parentheses after it, and put that limit, Lim, as n goes to infinity, of that inside sequence. 2 times n times pi over 1 plus n squared. All right. Is there a shadow? All right. Now, we've got to figure out this limit right here that's on the inside. Let's go over here to another part of our paper and figure this out. The limit as n goes to infinity of 2 times n times pi divided by 1 plus n squared. Now, I did a couple of examples last time on the trick on how to handle this. Let me repeat what the trick is. We look at what the highest power of n is. Look at what the highest power of n is. And divide every term by that power. and divide every term by that power of n, by that power of n. Okay, so on the top we have 2 times n times pi, so that's a power of 1, right, for n. On the bottom we have 1 plus n squared, so 2 is the biggest power of n. So what I do is here on the top I take my 2n pi and I'm going to divide that by n squared. Then I go to the bottom. I take my 1 and I divide that by n squared. Then I have a plus, and then I take my n squared and divide that by n squared. So everything gets divided by that power. Now let's figure out what we have here. Let's do a little simplifying here of this. The top term becomes what? I can cancel out an n, so I have 2 times pi over n on the top. The bottom, 1 over n squared, I can't do anything with that, but n squared divided by n squared cancels to a 1, plus 1. Okay. Now, let's look. Remember, we have n going to infinity. What is this top term going to go to as n gets bigger and bigger? 0. What is this term on the bottom going to? 0 also. What about the 1? It just stays 1. So this limit then is 0 on top, 1 plus 0 on the bottom, 0 over 1, the limit is 0. Okay? So let's go back then to the original problem here. So then we want to, so our limit on the inside then we determined was 0. So now we're just looking at the value of the tangent at 0 radians, and that is equal to 0, right. Sine over the cosine. And that's our answer. Okay? All right. Okay. There are a couple of facts here in this section that I want to or definitions also that I just want to tell you about. First of all, we have this definition. A sequence, A sub n, is called, quote unquote, increasing. Well, guess what? That's if each term is bigger than the preceding term. So therefore, if A sub n is strictly less than the next term. In other words, they keep getting bigger and bigger numbers. That's what it means to be an increasing sequence. Okay? Now, similarly then, a sequence A sub n is called decreasing if they get smaller and smaller. So in that case, A sub n is bigger than the one after it. A sub n plus 1. Okay? So, now, there's this other definition then, a sequence which follows from these two. A sequence is called monotonic. M-O-N-O-T-O-N-I-C. If it's either increasing or decreasing. If it's either increasing or decreasing. So that's, if you hear the term monotonic sequence, that means it's either going up or it's going down. It's one or the other. Okay. And then here's another definition of a bounded sequence. You know, a sequence has all these infinite number of values here, But sometimes the values are bounded by a top number and a bottom number. So a sequence is quote-unquote bounded if all of its values lay between two numbers that I'm going to call little m and big M. If every value of the sequence lays between those some pair of two numbers. Okay, so that just means it's bounded above and bounded below. And then there's a fact here that I want you guys just to be aware of. It's a pretty important theorem, actually, in what's called analysis. Every bounded monotonic, I'm missing a couple of syllables there, monotonic sequence converges to a limit. All right. I'll just give you a visual on this one here. Let's say we have a sequence that keeps getting bigger and 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 bigger. Can I do that all class? Let me just do that all class for the next hour. Okay, and yet there's a ceiling here. Oops. It never gets bigger than, say, this number 10. But it still keeps getting bigger and bigger. Never goes over the 10. This is first of all, it's a monotonic because it's increasing. It's monotonic. And it's bounded. It never gets more than the 10. And you can kind of visually see that it's got to have a limit equal to that 10. All right, just kind of visually. So that's what that fact is telling us. All right. Okay. All right. That's section 11.1. The big thing that you're going to find in homework is finding the limits of the sequences and whether they converge or diverge. That's what the homework is going to amount to. All right. Now we're going to go from a sequence to something called a series. So this is 11.2. And this is about what's called a series. All right. Basically, a series is where we take a sequence and start adding them together. Let's look at the number pi here. Pi, we know, is 3.14159 ... It keeps going on. So I can write this number pi like this. I can write it as 3 plus 1 over 10, 1/10, plus 4 over 100 for the 4, plus 1 over 1,000, plus 5 over 10,000, etc., like that. That's another way of writing that decimal. Notice here, this is an infinite sum of numbers. An infinite sum of numbers. And notice it has its sum, however, equals a finite number, pi. It equals a finite number, pi. Okay. All right. That kind of shows that we can have this kind of infinite sum that equals actually a finite number. So let's get more general here. Given a sequence, we'll call it a sub n. Remember, that's just an infinite list of numbers. if we add the terms of the sequence, i.e. a sub 1 plus the next term a sub 2 plus a sub 3 plus a sub 4, dot, 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 adding them all together, we get what is called a series. We get what is called a series. And the series is the summation, the sum, as, let's say, j equals 1 up to infinity of a sub j. So that's the way we can represent an infinite sum with that summation notation. And you guys have all seen that kind of index notation. All right. So it's really an infinite sum. Okay. All right. Now, we've seen already with the pi, we've seen that an infinite sum, can equal a finite number. All right. Okay. We're going to show this in a few minutes, but here's a fact. That if we sum 1 over 2 to the n, so our underlying sequence here is a sub n equals 1 over 2n. That's our sequence, but we're summing it now from n equals 1 to infinity. It's a fact that this whole infinite sum will equal the number 1. In other words, i.e., 1 over 2 to the first power plus 1 over 2 to the second power plus 1 over 2 to the third power, dot, 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 is equal to the number 1. Okay. And we're going to prove this, or show this in just a few minutes. Okay. Primarily what this section, what you're going to be responsible for in the homework is determining whether a series converges or diverges. Determine whether a series, not a sequence this time, but a series, converges or diverges. We'll give more specific a definition of that in just a couple minutes. Okay, to lead up to that, but that's what this section's all about. What we have to look at here, to do this, let's put it this way, to do this, we need to look at what are called partial sums. We need to look at what are called, quote-unquote, partial sums. What this means is that we're just summing a part of our series together. So let's say here, so say given a sequence, and we'll call it again that a sub n. Let what's called s sub 1 equal the first term of the sequence. But then s sub 2, let s sub 2 equal the sum of the first two terms of the sequence. Similarly, s sub 3 is going to be the sum of the first 3 terms of the sequence, etc. So these are partial sums. We're not summing the entire thing. So in general, if we let our subscript for the S be an N, then this is equal to A sub 1 plus A sub 2 plus dot, 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 plus A sub N, the first N terms of the sequence. And I can write this much nicer by saying it's the summation that sigma as j goes from 1 to n, not to infinity, of our sequence aj. And this is what we're calling S sub n. Each one of these is a partial sum. Each one is a partial sum. Okay. Notice then that these partial sums actually give us a new sequence. Because here now we have an S sub 1, an S sub 2, an S sub 3, an S sub 4, etc. So these partial sums give us a new sequence. Give us a new, I'll put that in quotes, sequence. And so it'll be in brackets little s sub n. So we've started with an original sequence, a sub n, of an infinite set of numbers, and we've now developed a new sequence, which is our s sub n. So let me put this here. Note, with a series, we have our underlying sequence, a sub n, that generates these partial sums. S sub n. And that, in turn, can be looked at as a quote-unquote new sequence in and of itself. So this, first of all, before we go on to the question on the concept of this partial sum. We're just summing up the first n terms of our sequence together. Okay, this gives us the ability now to look at a limit. Let's look at the limit of these partial sums. Okay, so we're talking about the limit as n approaches infinity. Now our partial sums are s sub n, right? Well, this equals the limit, again, as n approaches infinity. Now let me put in these parentheses what our s sub n is, and it's the sum of the underlying sequence from 1 to the number n. All right, it's the partial sum of the first n items. Well, here, if we're taking if this top n here is going to infinity, what we're really talking about here then is the summation from j equals 1 to infinity of our underlying sequence A sub j. And this is what our series is. Okay. So what we can conclude from this is this. We look at the limit of the partial sum. If it is a finite number, then our series, the whole infinite series, converges. If it isn't, it diverges. Okay, so definition. If the limit of the partial sum, i.e., limit as n goes to infinity of the f sub n, let me get rid of that parentheses, that's not going to work out. The limit of the partial sum as n goes to infinity, if it equals L, a finite number, then the series, the whole infinite series, which is the summation from j goes from 1 to infinity of the aj, the whole infinite sum converges to that L. Otherwise, it diverges. Otherwise, it is, another way we can say it, it is divergent. Or it diverges. Okay. All right. Why don't we take a 5-minute break here just to refresh ourselves and get moving, and then we'll continue with this. Yes, sir. Right. Oh, well, no, actually, that's like, I don't know. Okay, okay, is there anything more you can yeah. What I would suggest is actually let you go. So I think that we're just starting. I mean, I don't think that's something because everybody has that situation. But I think that having difficulties with some of us either not doing time purposes or significant. And I also crazy. Way out. Okay. So I know I have. Yeah, I mean, because I know humans. But that's what I would think that you need to do. Is do that. In fact, if you can, well, if you can do some of those, then I might not look at just putting this, but maybe take care of it. So they reach out and do that shot. You didn't get back in. No, I only handed back all the previous ones. I have not graded that last one. I have not graded before the exam. No, I don't. So I don't. That's good. It's just that extra practice. And then if you're stuck on something, you can email me and say, oh, I'm such a problem, I don't know what the heck to do, or I'm stuck at this point, and I'm pretty quick at responding back. Right? Right. Yeah. Thank you. Mm-hmm. I don't even care if I'm able to get some other questions, but this is supposed to be like a moment point here. Actually, page 2, 1.5. That's first 3. Oh, I see what you're saying. It has another. Yeah, oh, I gotcha. Right. One of I was kind of general what I took off. Yeah. It wasn't legal. Yeah. That's right. That was fun. That was fun having to do the subtracting and then adding. I lost track of it. Okay, I think we'll get started then. So we need to look at some specific examples here with series rather than just talking in kind of generalities. And the first example is going to be one of the most important series that you're going to need to know about. And it's called a geometric series. Put a little asterisk by this geometric series. This is where the underlying sequence a sub n is equal to this. Some number a, not connected with the a sub n, times some number r raised to the nth power. And we'll be looking at a couple of examples. This a, of course, doesn't equal 0, because that would be boring. Everything would be 0. And the r doesn't equal 0 either. Okay? So we're talking about this. We're talking about a sub 1 is equal to a times r to the first power. A sub 2 is equal to a times this r to the second power. A sub 3 is a times r to the third power, etc. Those are the terms, what the terms of the sequence look like. Now, the corresponding series then is this. The corresponding series is, okay, it's actually, let's see. Actually here, let's just put an a sub naught here. These, we're going to see here with examples that these things actually start with just plain a. So, excuse that, right there at the top, they're going to start with just plain a. So the corresponding series is that a, that's our first term, plus a times r to the first power, we're adding these together, plus a times r squared, plus a times r to the third power, plus dot, 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 and these all then equal, the whole infinite sum equals from n equals 1 to infinity, of A, notice every term has A in them. Now, R is taken to a power. The thing is, our first power of R here is really the 0 power, because anything to the 0 power equals 1. So therefore, here in our summation here, the exponent for R isn't going to be n, it's going to be n minus 1. So when n is equal to 1, then it's r to the 0 power. When n is equal to 2, it's r to the 2 minus 1, or 1 power. So the exponent there is n minus 1. Now, notice, though, that each term of the series is obtained from the previous one by multiplying by r. In other words, we multiply by r. Here, we're multiplying again by r. Etc. Each one is multiplying by r one more time. So let me put this statement here. Each term of the series is obtained from the previous term by multiplying by r. By multiplying by r. Okay. And this r is called the common ratio. Now, sometime towards the end of college algebra, you had a brief introduction to these series, this geometric series. How familiar you are with that is another story. Okay, this r is a common ratio. Now, we're going to do a little kind of general stuff before we get to some nitty-gritty, just regular problems. So bear with me here with this. What we're trying to find here is the limit as, say, n goes to infinity of this sum, j equals 1 to n, a times r to the j minus 1 power. That's what we're trying to find, the sum of this infinite series. Okay, now the partial sum f sub n is equal to what? It's equal to our a, our first term, plus our second term, plus our third term, plus all the way up to our nth term, and that'll be up to a r to the n minus 1 power. Notice that this altogether is n terms. So that's our first sum for Sn. Now what I'm going to do to this then is I'm going to multiply this partial sum by the common ratio. This is leading somewhere. So I'm multiplying this by our ratio of r. So this first term, a, is going to become a times r. Our second term, ar, is going to become a times r squared. And then we're going to go along. This term here is going to become a times r to the n power. Okay. Now, let's subtract the bottom from the top. And a lot of stuff is going to cancel out. So what we're doing is we're taking s sub n and we're subtracting from it the common ratio r times s sub n. And what we get is this. Our a term here is going to stick around. All these other middle terms are going to cancel out. What's still left over, though, is on the bottom, is this a times r to the nth power. So minus a times r to the nth power. So let's rewrite this we have a common term Sn here. So let me factor that out. And on the left side, I have f sub n times the number 1 minus r is equal to, and let's also factor out over here. We have an a here and an a here. Let's factor that out. And that'll be 1 minus r sub n. Okay, we're assuming r doesn't equal 1, so I'm going to divide both sides by 1 minus r. And so what I get is that our partial sum, f sub n, is equal to this formula. A times 1 minus r to the nth power, all divided by 1 minus r. All right. Now, at the beginning of class today, we said what this limit is. If that absolute value of r is less than 1, then this term here, the limit of r to the nth power, is going to be 0. That was at the beginning of class, as n goes to infinity. So, the limit of this partial sum is our series sum. Bear with me. Hang in there. The limit then, as our n goes to infinity, of our partial sum is equal to, well, what happens here? As n goes to infinity, that r sub n, r to the nth power, goes to 0 if the absolute value of r is less than 1. So then what we get then is a times 1 minus 0 over 1 minus r, or in other words, a over 1 minus r, if the absolute value of the ratio is less than 1. Okay. And this is then the sum of our whole infinite series, the sum from j equals 1 to infinity of a times r to the j minus 1. All right. So let me give you some of this in English here. Let's call this the bottom line. The nitty-gritty, the bottom line. Asterisk. The geometric series, starting with a, then plus a times r, plus a r squared, plus a r cubed, plus all the way to infinity, is convergent if the absolute value of the r is less than 1. Its limit, or sum, is equal to a over 1 minus r. Otherwise, if the absolute value of r is bigger than or equal to 0, it diverges. End of asterisk right there. All right. So this geometric series, as long as that common ratio is something between minus 1 and 1, but not including the minus 1 and 1, it's going to converge to a sum equal to a over 1 minus r. All right. Let's absolutely do an example here, okay? Let's look at that one that we talked about earlier, this summation as n equals 1 to infinity of 1 over 2 to the n power. Okay. Now, it helps to write out a first few of the sums, or the terms. Okay, in this one, n goes from 1 to infinity. So our first part here is 1 over 2 to the first power, plus 1 over 2 to the second power, plus 1 over 2 to the third power, etc. And this is, let me write it a little bit differently. This is 1/2 plus 1/4, 2 squared is 4, plus 1/8, 2 to the third is 8, plus etc. Okay. Now, this is a geometric series. When we get to the next term, what do we multiply the preceding term by to get to the next term? Okay, both of you are saying the same thing. Multiply the bottom by 2, but really you're multiplying the whole thing by 1/2, 1/2. So R is equal to 1/2 in this series. What is our A here? The A is the very first term of the series. 1/2, right. So, I recommend you write out the first few terms so that you can properly identify the A and R. Recommend you write out the first few terms so that you can properly identify A and R. All right. So our R here is 1/2. So does this sum, infinite sum or series, converge? Yeah, it converges. 1/2 is less than 1. The absolute value of R is less than 1 because R is equal to 1/2. Therefore, it converges. And the limit then is A over 1 minus R. So we plug in the A and we plug in the R. The A we found was 1/2 over 1 minus 1/2. So this is 1/2 divided by 1/2, and that's 1. All right? So therefore, this whole summation that's of 1 over 2 to the n, as n goes from 1 to infinity, that whole sum is equal to the number 1 by using our formula. Okay, does anybody have any question with that first example? Because we're going to have a couple more here. Because this is going to be a lot of the homework that you have is identifying this. Okay, let's look at another example then. Now this one's kind of interesting because it doesn't give you a specific formula for the series. Find the sum of 5 minus 10 over 3 plus 20 over 9 minus 40 over 27 plus ... All right. So this is an infinite sum. So therefore, it's a series. Okay, first of all, is it a geometric series? Is there a number R that each subsequent term that generates each subsequent term that is multiplied by a term? This is very awkward the way I'm describing this. Is there a number R that is multiplied by a term to generate the next term? So I want you to look at this and tell me if there's an R. Yes. Yes. And Will, what is it? Here's the first term. Here's the second. Okay. Here's the third. I know you didn't mean that. Okay. What can we multiply 5 by to get negative 10/3? I think I heard it. Minus 2/3. Let's look at that some more. Then let's have our negative 10/3. If we multiply negative 10/3 by negative 2/3, we're going to get positive 20/9, and we get our next term. Okay? And the same way, if we take the 20/9, multiply it again by negative 2/3, we're going to get minus 40/27. And we get our next term. So we have to identify what the R is for it to be a geometric sequence. So our R is negative 2/3. Now, therefore, if once we know that R is negative 2/3, the question is, does it converge? Yes? And Nelson, why does it converge?
Because the absolute value of R is less than 1.
Right. If the absolute value of that ratio is less than 1, it converges. And of course, the absolute value of minus 2/3 is certainly less than 1. It's 2/3. So we know this sequence converges. All right. So now we need to find the limit. And we know that the formula for the limit is A over 1 minus R. Now, A is the first term of the sequence, of the series. So A is equal to 5. Thank you. A is equal to 5. R is equal to, careful with this, a negative 2/3. All right? Right. So we have 5 over a double negative 1 over 1 plus 2/3. And let's just figure out what this is. So this is 5 over what? 3/3 plus 2/3 is 5/3 in the denominator. And when we divide by that fraction, that's the same as multiplying by the reciprocal. The 5's cancel out. So our sum is equal to 3 from the formula. Okay. Are we okay with that? We have to identify the A. We have to identify the R. And if the absolute value of R is less than 1, we use our formula there to get the limit. Okay, this one's a tricky one, I must confess. This one requires a little kind of tricky algebra. Okay. And I tell you what, I don't think I'm going to do it. It's not worth it. This is what I want to ask next. Well, actually, okay, let's do it. Okay, this is our sequence here, or series rather, sorry. 2 to the 2n times 3 to the 1 minus n as n goes from 1 to infinity. Now, what I tell you to do here is, with this thing, we have to do a little manipulating. Okay. Let's rewrite this as n equals 1 to infinity, now 2 to the 2n. And what I'm going to do with the 3 to the 1 minus n, I'm going to break it apart using the rules of exponents. I can break it apart as 3 to the first power times 3 to the minus n power. I'm just using the rules of exponents. And then I'm going to use rules of exponents again. Notice I have a 3 to the minus n power. Now I'm going to put it in the denominator. So I have the sum, 2 to the 2n times 3, and then in the denominator, I'm going to put that 3 to the n, but it's now going to be a positive n. If I go from a negative, if I go down to the denominator, I have to change the sign. All right. And then I'm going to do some more exponent trickery. 2 to the 2n can be also written as 2 squared in parentheses raised to the n power. Okay? When we take a power to a power, we multiply the exponents together. Times 3 all over 3 to the n power. Okay, I told you it was tricky. And so let me rewrite this again. Of course, 2 squared is equal to 4. So this can be rewritten as 3 times, I got that 3 there, 4 over 3 in parentheses. Notice both of these, top and bottom, are raised to the n power. So now I'm just combining it into a single fraction where I have the 4 to the n on top, the 3 to the n on the bottom as a single fraction. And that's how I'm going to leave it. All right. Now let's write out a few terms. Okay, when n is equal to 1, that's my first term, I have 3 times 4 over 3. But 4 over 3 is taken to the first power. And then plus, when n is equal to 2, I have 3 times 16 over 9, the squaring it. And I go from there. I won't write out any more. Okay. What does this first term simplify to? 3 times 4 over 3. 4, right? The 3's cancel out. So my A term, my first term of the series, is equal to 4. Now what's my common ratio? Here's my series right here. 3 times 4 over 3 to the n power. What does each term get multiplied by as I keep adding them? 4/3. So r here is equal to 4/3. But the absolute value of this r is bigger than or equal to 1, so this diverges. And we don't have to go any further with this, all right? Because the r is bigger than 1. All right. So we went through that one. So occasionally you have a little bit of tricky little algebra, exponent manipulation that you want to do first before you really can get an answer. All right. Here's a question. Find the sum of the series, and this is going to be a little bit different looking series, the sum from n equals 0 to infinity. Now notice here, this starts at 0. Sometimes the initial index can be a 0 of x to the n power, where the absolute value of x is less than 1. All right. So this is kind of different because notice we don't have any like regular numbers here. All we have is this variable x. Okay. Let's write out a few terms. And that's why this can be very helpful to do this. Okay, when n is equal to 0, we have x to the 0 power, and that's 1, right? Anything to the 0 power is 1. Now, when n is equal to 1, we have x to the first power, and then n is equal to 2, we're adding x to the second power. So I think that's good enough, actually, to write out a few of the terms. Now, first of all, what is our A going to be here for this particular series? 1. The very first term, we saw what it was by writing it out a little bit. A is equal to 1. Now, what's our R? What does each term get multiplied by? X. r is equal to x. But we're told that the absolute value of x is less than 1. We're told that that's what it's going to be. So therefore, since r is the same as x, the absolute value of r is less than 1. So therefore, it converges. Okay. The sum then goes to a divided by 1 minus r. So let's fill in what they are. A is equal to 1, r is equal to x. So the sum is equal to 1 over 1 minus x. Let me write this formula down here. And I'm going to put an asterisk by this. If the absolute value of x is less than 1, then this infinite sum of x to the n power, as n goes from 0 to infinity, is equal to 1 over 1 minus x. So we have this whole infinite sum, and it equals that one term there, 1 over 1 minus x. All right. Okay. I'm going to put a fact down here. The book proves this. I'm not going to go through the proof. But this is the fact. The series summing 1 over n as n goes from 1 to infinity is divergent. In other words, the limit is equal to infinity. Now, what is this? Let's do a first few terms. First few terms. Okay, when n is equal to 1, it's 1 over 1. Plus, and then the next term, when n is 2, it's 1 over 2. And then it's 1 over 3, plus 1 over 4, plus 1 over 5, etc. So that's what this sum is. This kind of series rather, is called the harmonic series. I looked in Wikipedia for why it's called harmonic series. It's kind of interesting if you want to look it up, but I'm not going to go through it. So notice please that this is not well, I know you're going to look it up. I know you are. This is not a geometric series. I don't have any common ratio to get from one term to the next. This is not a geometric series. But it's a harmonic series, and it diverges. So I want you guys, this little fact here, I'm also putting some asterisks by that I want you to remember that this particular sum is divergent. Okay. Now, so far we've been talking about converging, and we've been talking about geometric series. That's the real important type. We've looked at this harmonic series. And now I want to give you what is called a test for divergence of a series. All right. We have this one fact. If the series, this infinite sum, n equals 1 to infinity of a sub n, if it's convergent, then these particular terms have to be getting smaller and smaller and smaller and smaller. These a sub n's that we keep adding on to it have to keep getting smaller. Otherwise, this thing won't converge to a finite number. It'll just keep getting bigger and bigger. So my conclusion is, if it converges, then the limit of that a sub n has to equal 0 as n goes to infinity. Now, I can flip this around and write it a different way. If the limit of the a sub n does not equal 0, I'm flipping it around, it's called the contrapositive. If it doesn't equal 0, then the series, which is the sum of the a sub n's, then the series diverges. Okay. And we can use that to determine whether a series diverges. So bottom line here is this. If that a sub n that we keep adding on, if it doesn't go to 0, then the whole sum will diverge. So let's look at an example here of this. So here we have, say, show that this series, the summation as n goes from 1 to infinity of n squared over 5n squared plus 4, show that this diverges. All right. Now, this here is our a sub n, that formula. So let's look at the limit as our n goes to infinity of that formula, n squared over 5n squared plus 4. What's the trick I told you on how to handle this limit? Right, divide every term by the biggest power of n that we have, and in this case, that's the power of 2. So divide every term by n squared. Every term by n squared. So this is going to give us the limit as n goes to infinity. So we take the n squared on top, and that's going to be divided by n squared. We have the 5n squared, that's going to be divided by n squared. And then we have the plus 4, and that's going to be divided by n squared. All right. So let's do a little simplifying of this. On the top, n squared divided by n squared, that's equal to the number 1. On the bottom, we again have n squared divided by n squared, but we have a 5 there, so that's going to simplify to a 5. And then we have plus 4 over n squared. Now, we were talking about the number n becoming bigger and bigger whole numbers. What is this part going to go to? It's going to go to 0. The 1 is going to stay as a 1. The 5 is going to stay as a 5. So this limit is 1 over 5, 1/5. 1 over 5 does not equal 0. So since the limit of the an as n gets bigger equals 1 over 5, it diverges. Okay. Because we keep adding that 1/5 on, it's never going to converge to anything. Okay. We've got a couple more examples. We'll see what we can get through here with these. This example here is, I think, kind of interesting. I don't know whether you'll consider it interesting, but I think it's kind of interesting. Consider this sum here. We're summing from n equals 1 to infinity of this formula, 1 over n times, and still in the denominator, times n plus 1. And we want to know, does it converge or does it diverge? What happens here? All right. Guess what we're going to do here with this 1 over n times n plus 1? Well, maybe don't guess what we're going to do. We're going to do partial fractions with this thing. We're going to rewrite using, see, these things never really die. Rewrite using partial fractions. Okay, so let's do this. 1 over n, this is a full factoring, n times n plus 1. We're going to have an a over n times, that's the first factor, plus some b over n plus 1. All right. Now, I'm not going to go through the whole process here. You guys know how to do this kind of partial sum, but this is going to be, a is going to be equal to 1, and b is going to end up equaling negative 1. So this is 1 over n minus 1 over n plus 1 when I break it apart. So what we now have is this kind of a summation, as n goes from 1 to infinity, of 1 over n minus 1 over n plus 1. Let's write out, again, some terms. Very helpful thing to do. Okay, when n is equal to 1, we have 1 over 1 minus 1 over 1 plus 1 is 2. When n is equal to 2, then we have plus 1 over 2 minus 1 over 2 plus 1 is 1 over 3. When n is equal to 3, then we have plus 1 over 3 minus 1 over 4. And this process continues. And I think this is enough to see actually, I should have stopped this. Let's just stop. Instead of going all the way to infinity here, let's just stop this at some finite number j. So scratch out that infinity and just put a number j there. And then our last thing then is going to be, when we fill in the j, is going to be 1 over j minus 1 over j plus 1. This is going to be a partial sum. This is when n is equal to j. Now, everything except for the very first term and the very last term are going to cancel each other out. Notice the minus 1/2 and the plus 1/2, minus 1/3, plus 1/3, they're all going to cancel out. The only thing that's going to be left is the 1 at the very beginning and the last term, minus 1 over j plus 1. Everything else has gone away. So therefore, this is our partial sum. Let's call this f sub j is equal to that. Now, to find the limit, then, we do the limit as that partial sum goes to infinity. And in this case, the 1 is still going to stay a 1, but as j gets bigger and bigger, that's going to go to 0. So we found out here that this thing has a limit, and it's equal, sum has a limit, and it's equal to 1. This process of where you have things minus, plus, they cancel each other out, has a name in mathematics. It's called telescoping. It's like how you can fold up a telescope or the lens of a camera, depending on what you need it for. In this sense, a big string of things is telescoping down into only the sum of 2 things. And that's why it's called telescoping. Okay. I want to actually, just for a second here, go back to that harmonic series. Remember, that was the sum of 1 over n as n goes from 1 to infinity. 1 plus 1/2 plus 1/3 plus 1/4, etc. And this thing it shows in the book this divergence. Yeah, Jenna?
So the last one where it equals 1, where we just stop there, did you want to start with the divergence?
So if the limit is equal to a finite number, is it convergent or divergent? If the limit equals a finite number, convergent, right? I thought I heard you say divergent, but I know I couldn't have heard that. So it is convergent. The limit equals a finite number. All right. Back to this harmonic series, we're told, or it's showing in the book, that it's divergent. But this is our a sub n that we keep adding and adding onto it. I want to point out here that this limit of a sub n, as n goes to infinity, well, that's the limit of 1 over n as n goes to infinity, and so that's 0. So notice in this case, we have a series whose a sub n goes to 0, and yet it diverges. And yet it diverges. Okay. Back in this actual theorem or fact here that I gave you earlier, where is it here? Notice it says here, if the series is convergent, then the limit of the an equals 0. It does not say the opposite. It doesn't say if the limit of an is equal to 0, then it's convergent. What the opposite does say is if the limit doesn't equal 0, then it diverges. So we can have the an go to 0, and it still diverges. But we know for a fact if it doesn't go to 0, it will diverge, though. This still is a fact. Okay? All right. Yes?
Well, I'm confused because since the last one equals 1,
Mm-hmm.
not 0.
Oh, no. Okay, good question. Jen is saying, I'm really confused because, let's go back to this last one here, because we found that the limit is equal to 1. But this is what we found the limit to. This is the limit of our partial sum. The limit, that s sub j, that's the limit as what? N goes from 1 to j of the a sub n. That's our partial sum. And if that has a finite number limit, then the series converges. In this case, this is our original series here that we're talking about. This here, this is our a sub n. Okay? Now, the limit of, as we found out that this is a convergent, the sum is convergent to 1. Not the n term, not the a sub n. What is the limit as n goes to infinity of 1 over n times, in the denominator, n plus 1? N's getting bigger, 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 bigger in the denominator. The denominator is infinity, yes. 0. You've been saying it so well all along today in class. It's 0. So that's an excellent point that you're bringing up. The underlying sequence that's generating this sum, its a sub n does go to 0. But the whole sum of these terms, the series, it goes to a 1. So it's convergence. Do you get that? Okay, well, think about it, all right? It all has to do with the fact that we have an underlying sequence, and then we take the sum sums of the sequence to get the series. Right? Yeah. Okay. All right, we're pretty much finished. There's only like another example that we'll start with on Monday. And then 11.3 it won't take that long. I'm hoping that on Monday we can get through at least a good portion of 11.3, because I still want that homework to be due on Friday for that 11.3. So we're going to aim for that. Let's see. I guess that's it. Thanks, and have a great weekend, and let's hope we keep winning. Yes. Mm-hmm. Yeah.
Going through the framework.
Mm-hmm.
Somebody who has greatest factor denominator. Am I doing E right here?
Okay, so you're doing what you're putting up under here under the radical then is an n, because you're multiplying by 1 over n squared, right?
Yeah.
Mm-hmm.
So that's
Right. Yeah. So you have a 1 plus 1 over n. 9 minus 1 over n. Yeah, absolutely. Square root of 1/9 is 1/3. Yeah, you're absolutely correct. This is the correct thing to do. Then you're putting it under the radical, so it becomes an n.
Yeah.
Thanks for letting me. Oh, that's right. This is your take-home quiz. Thanks. Not a peep out of you guys.